Greetings and welcome to Distillate. In the previous class, we studied about vapor-liquid equilibrium, and I told you about two very important laws. The first law was the Raoult's law, which related the partial pressure of a component to the mole fraction in the liquid phase. And it said that partial pressure is equal to the product of the saturation pressure of that component into its mole fraction in the liquid phase. That is what the Raoult's law gives. And by a combination of Dalton's law and Raoult's law, we said that P is equal to sigma Pi, which is according to the Dalton's law, which is equal to sigma Pi naught Xi. And the second thing that we studied in the previous class was that Henry's law. We studied the Henry's law, and Henry's law again related the partial pressure of a component to its mole fraction, saying partial pressure is equal to Henry's law constant into the mole fraction in the liquid phase. All right, this was given by the Henry's law. So we also discussed that Henry's law would be applicable for very dilute solutions, that is when Xi tends to 0. And Raoult's law would be applicable when Xi would tend to 1. All right. This is what we discussed, and then we discussed certain numerical problems based on these. Today, we are going to deal with chemical reactions. Since we are all chemical engineering students, therefore, chemical reactions form a very integral part of the course. So while you'll be dealing with many subjects, you'll be having chemical reactions, and you'll have to go through different concepts like stoichiometry, stoichiometric coefficients and all that. So you need to be very clear with these concepts. All right. So this lecture is going to be a very important lecture. So please make sure that whatever is taught in this lecture, you clear with everything. So what is a chemical reaction? A chemical reaction is basically a way to represent a chemical change. All right. It includes the substances before and after the change, and the direction of change is shown by arrows. So let's say if a chemical change is taking place, which transforms A into B. This chemical change, it transforms A into B. Then this A and this B would be present in the chemical reaction, and the direction in which transformation occurs, that direction would be shown by an arrow. All right. So over here, A to B is a chemical reaction showing chemical change from substance A, that is the substance before change, to substance B, which is the substance after change. The direction of the arrow implies that A will change into B. All right. So whenever we have a chemical reaction, then towards the left of the arrow, we have reactants. And towards the right of the arrow, we have products. So towards the left, we have the reactants, and towards the right, we have the products. All right. So reactants are basically substances that are participating in the reactions, and the substances that would change. And products are the substances that are going to be formed in a chemical reaction. All right. So by convention, we write reactants towards the left and products towards the right. All right. Now, this is quite important. Whenever we consider a chemical reaction, there are a lot of informations that can be extracted from chemical reaction. All right. For example, let's take this basic reaction. AA plus BB gives CC plus DD. All right. If we take this reaction, then from here we can get the first information that we can get is reactants participating. And the second information, that what are the products that are participating. Okay. These two informations, as soon as you look at the reaction, you can identify. For example, if I have this reaction. This is the reaction of nitrogen and hydrogen to form ammonia. So over here, I can identify that my reactants are nitrogen and hydrogen, while my product is ammonia. All right, that can be identified. The second and very important information that the reaction would give you is that how many moles of each reactant is going to react to form how many moles of products. Okay, so this actually gives you a very important information. Let me tell you. So for example, if I take this reaction AA plus BB gives CC plus DD. All right. So this reaction is telling me that I have A moles of A. I have A moles of A. Okay. Whenever I have A moles of A, that means we require B moles of B. So whenever we want this reaction to take place, then for A moles of A, B moles of B are going to be required. Okay. These required moles are also known as theoretically required moles. Theoretically required moles. This is a very important term, theoretically required. So we'll be studying this further. For now, let's just keep this in mind that for A moles of A, we require B moles of B. Okay. And once we get all these things, then we'll get, that is, produced. So we'll get C moles of C and D moles of D. All right, this is going to be produced. So that means that if we have, let's say, 1 mole A, then that means it requires B by A moles of B, right? If A moles of A require B moles of B, then 1 mole of A would require B by A moles of B. It would produce C by A moles of C and D by A moles of D. All right. So this is a very important information that can be derived from a chemical reaction. On the basis of this particular information, we are going to do problem solving for chemical reactions. All right. In this particular reaction, A, small b, small c, and small d are known as stoichiometric coefficients. These are known as stoichiometric coefficients. All right. After that, the information that is provided by the chemical reaction based on the coefficients of different reactants and products in order to perform reaction-based calculation is known as reaction stoichiometry. All right. Then we have law of conservation of mass, which implies that mass can neither be created nor be destroyed. It can only be transformed from one form to another. So this law is basically applicable to the chemical reactions as well. So for example, if we have this particular chemical reaction, then in this chemical reaction, whatever would be the mass of reactants, whatever would be the mass of the reactants, the same would be the mass of products. All right, the same is going to be the mass of products. So when we'll be doing problems, one of the problems I'll help you to identify this particular law. All right, this particular law we'll start to identify. All right. So whenever we are doing stoichiometric calculations, just see this example. This is a very nice way. So we have this reaction 2A plus 3B gives C plus 2D. So it has reactants A and B, it has products C and D. So this particular reaction means that when we have 2 moles of A, then that requires 3 moles of B, all right, and that would produce 1 mole C and 2 moles D. All right, this is going to be the production. All right, so if I have 3 moles of B that are reacting, so 3 moles of B that are reacting, this implies that, sorry, I'm so sorry. Let us say for the above reaction, we need to find D formed when 9 moles of B are reacting. All right. So whenever 9 moles of B are reacting over here. All right. So we know that when 3 moles of B are reacting, then we require 2 moles of A and it produces 2 moles of D. Right. So if 9 moles of B are reacting, when we have 3 mole B, then we have 2 mole D. So when 9 moles of B, then we have 2 by 3 into 9 moles of D, right? Because if we have 3 moles of B produce 2 moles of D, then 1 mole of B is going to produce 2 by 3 moles of D, and therefore 9 moles of B are going to produce 2 by 3 into 9 moles of D. So on the basis of that, we are going to calculate the number of moles of D that are formed. So these types of calculations need to be done while we are dealing with stoichiometry. So let us do this problem. Nitrogen and hydrogen react to form ammonia. If 3 moles of nitrogen are reacting, find the mass of hydrogen reacting and mass of ammonia produced. If 10 kg of ammonia is produced, find the mass of nitrogen and hydrogen that have reacted. So let us start solving this particular problem. So keep this in mind that whenever you are solving a stoichiometric problem, a problem based on stoichiometry, the first step is to write the balanced chemical reaction. So we have nitrogen and hydrogen react to form ammonia. Therefore, the balanced chemical reaction that we are going to write is nitrogen plus 3 hydrogen gives 2 ammonia. All right. If you don't have a balanced reaction, then please, in the first step, you have to balance the chemical reaction. Only then you can proceed with stoichiometry. All right. Then, now we have 3 moles of nitrogen that are reacting. So since there are 3 moles of nitrogen reacting, let's do this A part. So 3 moles of nitrogen are reacting. All right. So moles of nitrogen is equal to 3 moles, right? 3 moles of nitrogen are reacting. All right. So we know that when 1 mole of nitrogen reacts, so it requires 3 moles of hydrogen and 2 moles of ammonia, correct? So when 3 moles of nitrogen are going to react, then how many moles of hydrogen will it require? 1 mole requires 3 moles. Therefore, 3 moles would require 3 into 3, which is equal to 9 moles of hydrogen. All right. And at the same time, since 1 mole of nitrogen requires 2 moles of ammonia, therefore produces 2 moles of ammonia, implies 3 moles of nitrogen are going to produce 3 into 2, which is equal to 6 moles of ammonia. All right. Then, once you are done with the calculations of moles, then you can go on to calculate the mass. So you have 9 moles hydrogen, implies mass of hydrogen is going to be number of moles into molecular weight of hydrogen. That is 18 grams per mole. All right. Sorry, 18 grams, not gram per mole. Gram per mole is the unit of molecular weight. And similarly, when you have 6 moles of ammonia, so that is equal to 6 into molecular weight of ammonia, that is 17, which is equal to 102 grams of ammonia. All right. So you have 18 grams of hydrogen and 102 grams of ammonia. Okay. This is how you are going to do your stoichiometry based calculations. All right. So pause the video and try to solve B part yourself. Hope you are able to solve this problem. If you've not been able to solve this problem, then let's do part B. But before I go on to part B, let's verify the law of conservation of mass for part number A. So for part A, we have got 3 moles nitrogen are reacting, which implies we have 3 into 28, that is 84 grams of nitrogen that is reacting. All right. We have already calculated that mass of hydrogen that is reacting is 18 grams. And we have also calculated that mass of ammonia that is produced is 102 grams. As I told you, that law of conservation of mass states that mass of reactants would be equal to mass of the products. So mass of the reactants is equal to 84 plus 18, which is 102 grams. And the products, that is ammonia, it is 102 grams. Therefore, the law of conservation of mass is verified. So let me tell you that law of conservation of mass is always verified for every chemical reaction. That is how this concept of stoichiometry has been formed. All right. Now let's do part B. So for part B, I know that we have 10 kg of ammonia. Whenever we have mass in stoichiometric problems, whenever we have mass, you calculate moles from that. Because every calculation in stoichiometry is done on per mole basis or kilomole basis. So that is why you have to calculate moles. So molecular weight of ammonia is 14 plus 3, that is 17. Hence we have 14 by 17 kilomoles of ammonia. All right. Now we know that by stoichiometry, nitrogen plus 3 hydrogen gives 2 NH3. That means when 2 moles of ammonia are formed, then we have 1 mole of nitrogen reacting and 2 moles of hydrogen, 3 moles of hydrogen reacting, right? Therefore, 10 by 17 kilomoles of ammonia is actually equal to 10 by 17 into 1 by 2 kilomole of nitrogen, right? And that is equal to 10 by 17 into 3 by 2 kilomole of hydrogen. All right. And then when we calculate masses, then we multiply kilomole by molecular weight. So this multiplied by 28. Therefore, mass of nitrogen that is produced, we'll get it as 8.235 kg nitrogen. All right. Similarly, we'll over here get 10 by 17 into 3 by 2 into 2. So that is 1.765 kg hydrogen. All right. So hope you people have got this, right? Then we move on to example number 2. We have carbon dioxide which reacts with carbon to produce carbon monoxide. So the stoichiometry of this particular reaction is given by carbon dioxide plus carbon gives you, this is the reaction. All right. So that means 1 mole of carbon dioxide requires 1 mole of carbon to give 2 moles of carbon monoxide. All right. So when we have 100 grams of carbon dioxide, so what is the moles of carbon dioxide? 100 by 44 moles of carbon dioxide is equal to 100 by 44 moles of carbon, which is equal to 100 by 44 into 2 moles of carbon monoxide. That is equal to 100 by 44 into 12 grams of carbon, which is equal to 100 by 44 into 2 into 12 plus 16, that is 28 grams of carbon monoxide. All right. So this is going to be equal to 27.273 grams of carbon, which is equal to 127.27 grams of carbon monoxide. All right. So that is the answer. 27.273 grams of carbon and 127.27 grams of carbon monoxide. All right. Then please pause the video and try to solve this problem yourself. Now, hope you people have managed to solve this problem. If you haven't, then let's see. Hydrolysis of ethene leads to the formation of ethanol. Ethene is C2H4. Hydrolysis implies water is added, and this gives us ethanol, which is C2H5OH. This reaction is balanced. All right. So we'll go on to solve the problem further. So as I told you, we have to always take moles first of all. So we have 778 kg ethanol implies 778 upon molecular weight of ethanol. That is 12 into 2 plus 5 into 1 plus 16 plus 1. That is 46 kg per kilomole. So that gives us the moles of ethanol that have reacted. Now from stoichiometry, you can say the same amount of moles have reacted for ethene as well. So we have 778 by 46 kilomole of ethene have reacted to form 778 by 46 kilomoles of ethanol. Now, when we multiply this by the molecular weight of ethene, molecular weight of ethene is nothing but 12 into 2 plus 4, that is 28 kg per kilomole. So that gives us the kg of ethene that must be provided. So 778 by 46 into 28, which gives us 473.565 kg. All right, 473.565 kg of ethene. This is the amount of ethene that needs to be provided in order to produce 778 kg of ethanol. Let's move on to the next problem. Pause the video and try to solve this problem yourself. Hope you could solve this problem yourself. If you haven't, then please look at the solution. How many moles of butane gas reacts to produce 0.125 moles of water during complete combustion? How many moles of oxygen gas react? So let's see. We have butane. Butane is C4H10. All right. This is butane. This reacts with oxygen to produce carbon dioxide and water. This is the reaction for complete combustion. All right. So when we balance this reaction, we are going to get 8 CO2, which implies 2C4H10, which gives you 10 H2 and 13 oxygen. All right. This is the balanced chemical reaction. All right. This is going to be the balanced chemical reaction. Now, once we are done with this, then we are going to solve the problem. So it is given that we have 0.125 moles of water. These are 0.125 moles of water. So when 10 moles of water are produced, then 2 moles of butane have reacted, right? That means when 1 mole of water is produced, 10 mole water implies 2 mole butane, which implies 13 moles of oxygen, right? So this means 1 mole water would imply 2 by 10 moles of ethane, 2 by 10 moles of butane, which would imply 13 by 10 moles of oxygen. Therefore, 0.125 moles of water would imply 2 by 10 into 0.125 moles of ethane, which is equal to 2 by 10 into 0.125, which is going to be equal to 0.025. All right. And then this is moles of butane, and that is equal to 13 by 10 into 0.125, which is equal to 0.1625 moles of oxygen. All right, so this should be your answer. 0.025 moles of butane and 0.1625 moles of oxygen. Then we come to the fifth problem. Pause the video and try to solve this problem yourself. Hope you could solve this problem. If you haven't been able to solve, then let's see how it's solved. In the combustion of heptane, CO2 is obtained. So let's do combustion reaction of heptane. So heptane is C7H16, CnH2n plus 2. So C7H16 plus oxygen gives you carbon dioxide plus water, right? So 7 CO2 and 8 H2O. Therefore, we get 11 oxygen, right? So this is my balanced chemical reaction. Now they have given that it is desired to produce 500 kg of dry ice and 50% of carbon dioxide can be converted into dry ice. So if we have 500 kg of dry ice, that means it is 50% of carbon dioxide that has been produced. Therefore, carbon dioxide would be 500 upon 50%, which is equal to 1000 kg, right? So CO2 is going to be equal to 1000 kg. So this is 1000 kg. All right. So the kilomoles of carbon dioxide are going to be mass upon molecular mass, that is 44, right? So this is the kilomoles of carbon dioxide that are produced. All right. So now by stoichiometry, we can say since 1 mole of heptane produces 7 mole carbon dioxide, that implies 1 mole of carbon dioxide is going to be produced by 1 by 7 mole of ethane, heptane, right? 7 mole carbon dioxide is produced by 1 mole heptane. Therefore, 1 mole carbon dioxide is produced by 1 by 7 mole of heptane, right? This 1 by 7 mole of heptane is there for 1 mole of carbon dioxide produced, right? So if we have 100,000 by 44 kilomole of carbon dioxide, this 1000 by 44 kilomole is produced by 1000 by 44 into 1 by 7 kilomole of heptane, right? So 1000 by 44 into 1 by 7 kilomole of heptane is equal to the kilomoles of heptane required. All right. Therefore, mass or weight of heptane is equal to 1000 by 44 into 1 by 7 into, what is the molecular weight of heptane? 12 into 7 plus 16 into 1. That is equal to 100, right? Therefore, we get the answer as 324.675 kg of heptane. This is the amount of heptane that is required. All right. So these were the basic classes that involved certain basic concepts that would be used in chemical engineering. So we studied about moles, mole concept. We studied different chemical engineering variables. We studied about molarity and molality, mole fraction and mass fraction. Then we studied about ideal gas equation and how to apply the ideal gas equation in different conditions. After that, we studied about how to convert things from mole percent to weight percent and weight percent to mole percent. Apart from that, we also studied about certain concepts like vapor pressure, partial pressure. Then we dealt with vapor liquid equilibrium, in which I gave you introduction to two very important laws, Raoult's law and Henry's law. And finally, in today's lecture, we discussed about stoichiometric calculations, about how to do calculations using stoichiometry of a chemical reaction. So this was all what are the basic concepts that are involved in chemical engineering. From the next lecture, next video onwards, we'll be dealing with chemical process calculations. This, from now, we are going to start with the chemical engineering subjects. So before you start going through the chemical engineering subjects, make sure that these concepts that you have been taught, they are very clear. So watch these videos again and make sure that these concepts are clear before you start studying the chemical engineering subjects.